So this question says to complete and balance the precipitation reactions, include physical states in your equation. Click here for solubility rules. I'm going to use the solubility tables from the text just because this is a screenshot, and if I click this it won't bring up the solubility rules. But you would definitely want to use the solubility rules that Sapling provides for you to make sure that you have all the rules that they're going to expect that you have. So we know it is a precipitation reaction. They're telling us. And I see barium nitrate aqueous plus copper 2 sulfate aqueous. I'm going to start with that reaction. Precipitation reactions are a kind of reaction known as double replacement, or sometimes known as metathesis. And basically what happens is the ion switch. So here we have a cation and an anion, barium nitrate, and here a cation, copper 2, and sulfate is our anion. When both of these are put in water, and I forgot to put the aqueous there, but it's there in the original problem. When we put these two solutions together, what they're going to do is the ions, this cation is going to have an opportunity to interact with the anion of copper 2 sulfate, and this cation is going to have an opportunity to interact with the anion from the other compound. So basically what we're doing is we're switching cations and anions. Barium plus 2 was originally with nitrate, and now it's going to switch to sulfate. Copper plus 2 was originally with sulfate, and it's going to switch to nitrate. So the first thing we want to do is we want to figure out what the formulas of the products are going to be. To do that, I separate out my first compound into the cation barium plus 2 and the anion nitrate. You have to know what the charges are. Barium is an alkaline earth metal and always has a charge of plus 2, and nitrate always has a charge of minus 1. Here, copper can have a variable charge, but because sulfate always has a charge of negative 2, we know that copper has a charge of plus 2. So I separate out the cation and the anion for each compound, making sure that I write the correct charge in the upper right-hand corner. The next thing I do is I switch. I switch this cation with this anion and this cation with the other anion. And I figure out what the formula of the product is going to be. So barium has a charge of plus 2, sulfate has a charge of minus 2. This is our formula. They cancel each other out in a 1-to-1 ratio. Copper has a charge of plus 2, nitrate has a charge of minus 1. This is the formula for copper 2 nitrate. There have to be 2 nitrates to cancel out that positive 2 charge. The next thing that I do after I figure out what the formula of the products are is I look at the solubility guide. So I'm going to bring up this solubility guide. Let me make this a little bit smaller so we can see it. This is the solubility guide from the textbook. And so I'm going to take a look at barium sulfate. I'm going to figure out whether that is soluble or insoluble. So here's sulfate. Sulfate is in the soluble section except when it's paired with strontium, barium, lead 2, or calcium. So that means it's insoluble. So I go back to my work. Barium sulfate is going to be a solid. It will not be soluble. It won't dissolve in water. That's going to be its phase. Copper 2 nitrate, if I look at the solubility guide, I see that nitrates are always soluble and there's no exceptions. So I know that my copper 2 nitrate is going to be AQ. So now I know what the states are of my product. So barium, aqueous barium nitrate, reacting with copper 2 sulfate, which is aqueous, will form solid barium sulfate and copper 2 nitrate aqueous. So I want to make sure that my equation is balanced. I have 1 barium, 2 nitrates, 1 copper, 1 sulfate, and 1 sulfate. The next problem is aqueous potassium phosphate plus aqueous magnesium chloride. So I've rewritten this, the reactants up here, and I know it's a precipitation reaction, so I know my ions are going to switch. This cation is going to be placed with this anion, and this cation is going to be placed with this anion. So the first thing I do is I take apart the ions that make up each compound. So potassium phosphate is made up of potassium as well as phosphate. Notice I don't put the 3 here. I'm interested only in the charge of my potassium, not how many there are. I'll balance this 3 at the very end of the process. All I care about is the charge. My phosphate has a -3 charge. Magnesium always has a +2 charge. It's an alkaline earth, and chloride has -1. So when I switch these two, potassium and chloride each have a charge of 1, +1 and -1, and they cancel each other out in a 1-to-1 ratio. So this is the formula of their product. Magnesium and phosphate don't have charges that cancel out in a 1-to-1. Magnesium is +2 and phosphate is -3. So to get the charges to cancel out, I need 3 magnesiums, which gives me a total charge of +6, and 2 phosphates, which gives me a total charge of -6. So Mg3PO42. Those are the formulas of my products. It doesn't matter what order I put them in. I can put potassium chloride first or magnesium phosphate first. Doesn't matter their order. Next thing I want to do is I want to check the solubility. I'm going to look at magnesium sulfate first. Magnesium phosphate first. All right, so phosphate, here's phosphate. Phosphate is always insoluble. Here are the exceptions. Magnesium is not one of the exceptions. So I know that magnesium phosphate is going to be solid. It doesn't dissolve in water. Potassium chloride, if I look at my solubility guide, anything with potassium is always soluble. There are no exceptions. So I know that that's going to be aqueous, which means it dissolves in water. So potassium phosphate aqueous plus magnesium chloride aqueous forms solid magnesium phosphate and aqueous potassium chloride. The next thing I want to do is I want to balance my chemical equation. I notice that I have 2 phosphates here. So I need a coefficient of 2 for my potassium phosphate. So now I have 2 phosphates on my reactant side and 2 phosphates on my product side. I also have 3 magnesiums on my product side. So I put a coefficient of 3 in front of my magnesium chloride. Now I have 3 magnesiums on my reactant side and 3 magnesiums on my product side. Lastly, when I put these coefficients of 2 and 3 in front of potassium phosphate and magnesium chloride, this 2 changed how many potassiums. I now have 6 potassiums, and this 3 changed my chlorides. I now have 6 chlorides. So I need a coefficient of 6 in front of my potassium chloride, so it will be balanced. And again, aqueous, aqueous, solid, and aqueous.